So this is probably going to be the most important video of this chapter, because I'm going to give you a step-by-step recipe for calculating all of the possible surface integrals that you might be asked to calculate. Okay? Now, the first year I taught maths, I didn't give this step-by-step recipe, because that's not how books explain surface integrals, and that's not how I was explained the surface integral. But then, on that first year, students always came up with the same sort of questions. And I realized that the questions came from the fact that I teach you how to calculate ds, I teach you how to find the limit, I teach you how to do all of the different elements, but I never do a list of the things you have to do and in which order. So students, sometimes you might become a bit lost. So I decided that I would do this step by step. It's like a manual that you can follow. Now, this manual makes it seem like doing a surface integral is more complicated than it actually is. However, I think it's really helpful when you are beginners. So that is your case. This is the first time you are doing surface integrals, so you are beginners. So it makes perfect sense to follow a step-by-step procedure. But bear in mind that in practice, in your future, whenever you are calculating a surface integral, you will likely not use this step-by-step procedure. You just have understood all of the concepts of surface integrals, so you will just do it. Okay? That's like the first time you were learning how to expand two brackets, and you were given a step-by-step, do this times this, then do this times this, and you could write the steps. And now whenever you expand a bracket, you just expand it. You don't have to think about the individual steps, right? So with experience, you can start forgetting about this step-by-step recipe. But as beginners, this is very useful. So I please ask you to, if you see that you are confused with surface integrals, please follow this recipe. You will never fail if you follow this recipe. Okay? So here it goes. Our aim is to calculate a surface integral on some surface S of a function which in the most general case is going to be a function of position times ds, the differential of surface. Okay? Now, next to every step, which I'm going to write on the left-hand side of this page, on the right-hand side, I'm going to write an example, so that whenever I write the step, you see the example. So the example would be, for example, that surface S, I have to specify what surface it is. For example, a sphere of radius r. Sorry that I'm blocking the writing, but it says sphere of radius r. And then the function f of r is whatever you want to integrate. Okay? For example, I might ask you to calculate the double integral or the surface integral of x squared ds. Okay? And you might wonder, why would you want to integrate x squared ds? Well, maybe x squared is the density of the sphere. Okay? So maybe the density is a function that depends on x, y, z, and the density of this sphere is x squared. And then you want to calculate the total mass. So the mass is the double integral of the density times ds. Okay? Now, in earlier videos, I said that the integrand, so whatever is inside the surface, is usually written as a function of the two parameters of the surface. But actually, it can also be written as a function of r. And later, I will show you that one of the steps will be to convert this function of r into a function of the two parameters. So that will be one of the steps. Okay, so this is what we want to calculate. So first step, define the parametrization of the surface. So this means that you have to write a vector r as a function of two parameters. And this is the same as writing a vector of x as a function of u and v, y as a function of u and v, and z as a function of u and v. In the examples I showed you, I typically used cylindrical or spherical coordinates, so you know what x, y, and z are, and I fixed maybe the radius, I fixed it to capital R or something like that, yeah, but I always started with giving 3 equations to define the surface. And you should also give the limits in U, so U maybe goes from A to B, and V goes from C to D. So the limits of this surface, okay? Do not forget to specify the limits, please. So you specify the equation, but also you need to specify the limits of the integration. Okay, second step. Let me color like this. So second step would be to find the surface differential. ds. Okay, how do you do it? There were different ways. The first way is look it up or remember it, or from memory. And this is the case, for example, if you are doing a sphere, you should know that ds in a sphere, maybe by having done so many problems, I know you will do lots of problems. So eventually you will automatically say ds is r squared sine theta d theta d phi. And you will write this automatically. Okay, and that's fine. You can write it from memory. That's perfectly fine. If you don't remember it or you cannot find it in a table, you can derive it by geometrical intuition. And you remember that the way to do this was to fix u and v to a certain value. Then imagine that you increase u and v by an amount du and dv respectively. And then you have to find the area of this square. And the area of this square is ds. That's how you do it geometrically. Sorry that I blocked that. Yeah. So that's the geometrical intuition method. And thirdly, you apply the recipe to calculate ds. So calculate it using the equation. And what is the equation? You will use it so often that eventually you will just remember it. It's the partial derivative of r with respect to u, cross product the partial derivative of r with respect to v. After you do the cross product, you take the norm, which means the square root of the squares of the components, and then times du dv. Okay, so this will be ds. Remember that in order to calculate this partial derivative, you just have to look at this vector and do the partial derivative with respect to u. Okay, so this will be a vector, this will also be a vector, so you can do the cross product. Perfect, so that will be step 2. You have those 3 options. Step 3, and this one is new. I haven't spoken about this step yet. This is evaluate the integrand at the surface. This step is actually so important. I cannot overemphasize how important this is. So what is the integrand? So the integrand is f of r times ds. Okay, so the integrand is whatever is inside of the integral. So this is the integrand. Okay, so you need to make sure that this integrand is evaluated at the surface. What do I mean by this? So what I mean by this is that you have to substitute the fact that r is a function of u and v. Okay, so therefore your function f, which is a function of x, y, and z. Okay, so let me write it. This is a function maybe of x, y, and z times ds. You need to write it as a function of x as a function of u and v, y as a function of u and v, and z as a function of u and v times ds. Okay, so let me give you an example. In this example here, I said I want to integrate x squared ds on the sphere. So how can you do that? So if this is a sphere, x squared ds. So S is a sphere. So the equation for a sphere is the following. This is the parametric equation of a sphere that you would have written in step 1, okay? And the two parameters are theta and phi. So now I want you to evaluate the integrand, which is, so ds, you already got it. It's r squared sine theta, and that's already evaluated in terms of the parameters, theta. But you still have to evaluate x squared at the surface of a sphere. So how do you do that? Well, it's easy. So x is this. So the x value at every point in the sphere is given by this. So you need to do this squared. So you need to substitute x squared equals r squared sine squared theta sine squared phi. And this is the integrand that you will need, okay? Times ds. So you will have to do the double integral of x squared ds. That will be the double integral of this thing times ds, which is r squared sine theta times r squared sine theta d theta d phi. Okay, so we evaluated the integrand x squared in the surface by substituting, by looking at the parameterization vector r and substituting x. Okay, if the equation had x squared plus y squared, then you have to do this squared plus this squared, and so on. Okay, so this is the third step, and it can be written mathematically like this. You basically substitute x as a function of the two parameters, y as a function of the two parameters, and z as a function of the two parameters. And then fourth, you perform the double integration. And this is great because when you arrive at this step, so you started from here and you have ended up here. So you have your function, which is now a function of the two parameters, u and v. Okay, we could say that this becomes now a function of u and v, the two parameters. So you have a function of u and v. Then you have ds, which is also a function of the two parameters, du, dv. So this is ds, which is a function of u and v. So when you arrive here, which is the example here on the right, yeah. So you have the function, which is a function of theta and phi, which are your two parameters, u and v. And then you have ds, which is also a function of theta and phi. In this case, only theta. So you now have something that you can integrate because this only depends on theta and phi, in this case u and v. So the only thing remaining is to write the limits. The first integral corresponds to the limits of u, so those were a to b, and then the limits of v were c to d. So now you are ready to integrate this. So one sanity check that I would ask you to always do before starting integrating things. So even before you start integrating anything, when you arrive at this step 4, please check that all that is inside of the integral, this is called the integrand. So this integrand must only contain u, v, and constants. Okay? Must only depend of u and v. If there is an x or a y or a z inside there, you're doing something wrong. You have to substitute x, y, and z by their values at the surface, by substituting the equation of the surface. Okay? So always make sure that this integrand must only depend on u and v, and maybe constants. So any constant that don't depend on where you are around. Okay? And once you arrive here, then it's very easy because you have a function of u and v, du/dv, so you just do the double integral. Okay, so that's the step-by-step recipe. 15 minutes of video. I hope I was clear. I did it quite slowly, so now we have this recipe to do double integrals. Thanks for watching, and let's do some examples.